Hello, my name is Jack Mosley, and this is optimal control of a ball pitching robotic arm. We're going to use a couple different control algorithms to teach a two-joint arm to throw at a target. The two main goals of this project are to find the optimal trajectory from the origin to the target point for a flying projectile, and to find the optimal input to control a robotic arm to achieve this optimal trajectory when it throws a ball. This project is based on this quote here. The general hypothesis that natural structures and processes are optimal is one of the fundamentals of bionics. So we're going to test this hypothesis by seeing how similar the throwing motion we achieve here is to the throwing motion that humans use. So like I just said, the first goal of this project is to minimize the optimal launch trajectory to throw the ball at the target while minimizing the energy needed. We use the least action principle as a starting point, where we seek to minimize the integral of the kinetic energy minus the potential energy. In our case, we're going to use this vx squared, vy squared, alpha t squared term as the cost function to minimize. 1/2 vx squared plus vy squared is the kinetic energy of the projectile, and alpha t squared term is added if we want a trajectory that hits the target in less time. We can scale this alpha term depending on how much we care about the energy versus the final time. When we solve this, the three variables we're trying to find are the initial x and y velocity and the final time. So now we can go take a look at Matlab and see how we solve this problem. First off is the cost function that we use. This first one ignores the time, so it only cares about the energy. The second one includes the time. Next, we look at the nonlinear constraint function. This takes the initial position, 0, 0, and the initial guess for the velocity and final time, and then it simulates the trajectory with the projectile dynamics that we see down here. The nonlinear constraints also include the boundary condition that we want the final x and y coordinates to be at the target point that we see here. Finally, we can solve, or I'll talk about the projectile dynamics briefly. So x depends on the x velocity, which is this one. Y depends on the y velocity, which is the fourth state. The acceleration in x is 0, and the acceleration y is just gravity. And then we can solve the problem in Matlab with the command fmincon. And I've solved it twice for both cost functions. This first one ignores the time. The second one is going to be a slightly more direct shot because it does care about the time. Now let's pop back over the presentation. So now that we know our optimal launch trajectory, we can teach the robotic arm to achieve that result. This is the model for the robotic arm. There's two joints and one input for each joint. The states for the system are the angles and the angular velocities of the two joints. Also here at the bottom is the relationship between the velocity and the states. We can use this to translate the desired velocity into states at the beginning of our process, and then translate the states back into velocity at the end of the process to visualize our results. For the final two reference states, I set theta1 to be 3 pi over 4 and theta2 to be 0. So the arm is straight and pointed in a 45-degree angle forwards when it releases the ball. The cost function, the cost functional, is the objective we want to minimize. Included in this is the running cost, which accumulates over t0 to t1. In our case, the running cost is the sum of all states squared plus the sum of all inputs squared times a weighted term beta. Next is the terminal cost, which is added at the end. The terminal cost is set to be the difference between the final state and reference state squared. So in order to minimize the cost, the algorithm has to drive the final state as close as possible to the desired state. Lastly, we have the state function, which is taken from the states we set on the previous slide. With the cost functional set up, we can derive the equations we use for gradient descent. So the state equation and initial state we have already found. The optimal input equation we can find by taking the derivative of the running cost and state equation with respect to u. We can create the Hamiltonian as shown. which gives us a simple form to derive the co-state equation from, and then we can take the derivative of the terminal cost function with respect to x to find the terminal co-state. Now that we have the initial conditions, the target, and the model for the system, let's take a look at how the ARM performs in Matlab. So this is the Matlab code to run the simulation. There's a more complex code we'll look at a little later, but for now, let's just look at the results. We can see the angles are driven to the desired states of 0 and 3 pi over 4. The angular velocities are also driven to the desired states based off the relationship, the v equals L times theta dot cosine theta or sine theta. And then we can see the evolution of the costate, the optimal input, the evolution of the cost, the difference between the x and y velocity that we find with the reference x and y velocity, which it's not exact, but it is pretty close. And then we can plot the trajectory that results from it, which doesn't land exactly at our target of 10.2, but again, it's pretty close. And lastly, we look at the optimum movement of the arm as it's making its throw. So we can see from this plot of the angles previously, and it's really obviously here, that there's a big issue with the angles that the joints are at throughout the movement. The goal is to achieve humanoid locomotion, and this is very far from that. Both joints do several revolutions, which is an issue particularly for the second joint, because a human elbow can only has a range of 180 degrees, not 510 degrees. So from this we know we need to constrain the states. And we come back to the presentation. So we know in the case with constrained input that we can simply clip the input if the dynamics set it to a value higher than its bounds. So maybe we can do the same thing with the states. I added an event function to the state iterations ODE to stop and restart every time the states try to exceed bounds. On the left, it stops when theta 2 is less than pi. On the right, it stops when theta 2 is greater than 0. Long story short, it doesn't work. We can see from the plots that this process creates massive vectors of hundreds of points that take a long time to solve, and the dynamics aren't converging towards our target state. So this is no good. We can't just clip the states, so we have to find a different way to constrain them. Here, we'll constrain the states by adding a penalty function for going beyond the bounds. The penalty function is added to the running cost function, and it makes it more expensive to go into states beyond the bounds. So like if theta 2 equals 100, 100 times mu is getting added to the cost. Theoretically, gradient descent should drive the arm away from these states since they're much more expensive and keep the arm within the bounds. Since we've updated the running cost, we also have to update the p dot function. We use a piecewise function to add onto the p term corresponding to theta 2. I've mentioned and shown a few different weighting variables throughout this, and at this point, the challenge to finding the optimal control solution is tweaking the different variables. So I set Q very low because we don't really care how big the states are while the robot is moving. I set mu very high because it represents physical constraint on the system that we can't defy. We have to be careful though, because if we set mu too high, then the descent will ignore all the other constraints and just focus on satisfying the boundary conditions. And then I set gamma high because it's important that the final state is as close as possible to the target state. Lastly, I set beta to be low because although we do want to minimize the input, we're more concerned with how the system is behaving than we are with the input being low. So now let's take a look at the full Matlab code and see how that runs. We come down here to the beginning of the function. So first we see the function which calls the state equation. Below that is the code related to the event function, which clips the state to the bounds. I actually have the function set so that it'll never trigger, since triggering it would greatly increase the runtime. So this is effectively not here, but I left it in anyways just to see what it looks like. Because these aren't actually turned on, the states can exceed the bounds while the robot is learning. But as we'll see in a second, the final result does conform to the constraints. Next, we see calling the terminal costate, the costate function, and the optimal input equation. Now let's go take a closer look at all these functions. So x dot is pretty simple. We calculated that fairly early on. That hasn't changed. P dot has changed because we modified the running cost. I've also added here a penalty on the theta dots in case the arm is trying to go even further out of bounds if it's already out of bounds. And then this update U term, which includes the alpha for gradient descent, so it steps in the right direction every iteration to minimize the cost. For the cost evaluation, we have the running cost here, which includes this penalty function times mu, and then we have the running cost of the input times beta, and then we add the terminal cost onto that at the very end. And then, like I said, this is the event function that we've effectively erased, but it's still there anyways. So it'll step if theta 2 is greater than negative 10 pi, or if theta 2 is less than negative 10 pi, it'll stop the ODE. And then lastly is z dot. We saw that for the projectile motion. So let's see what this does to the results.
We can see that the angles are driven to 3 pi over 4 for theta 1 and 0 for theta 2. Theta 1 is bounded to negative pi and pi. Theta 2 is bounded to negative pi and 0. Both angles stay within their bounds. We can see that the angular velocities also converge. Then the evolution of the costate and the optimal input. The input is interesting. For the unconstrained case, we saw that the input slowly increased over time, making the arm do several revolutions. In the constrained case, because it can't go negative, it's going to slowly build up and then greatly accelerate at the end, right before it throws the ball. And then the evolution of the cost function, and then we can see the x and y velocities that we computed compared with the reference x and y velocities. It's not as accurate as in the unconstrained case. Part of that is because I had to reduce the number of iterations for this, so it's not completely converged, but it's somewhat in the ballpark. And then, like we would expect, because the x and y velocities are off, the projectile doesn't land exactly at the target we want of 10.2. And then lastly, when we look at the motion of the arm, obviously not completely human, but it's not wild and out of control like it was before. It's much more reasonable, recognizable as a throwing type motion.
Obviously, the arm and the human throw have some pretty big differences because the arm doesn't have a body and humans have weird joints. But we can still see some similarities in the two movements. The robotic arm moves from a starting point to a point as far as possible away from the target state, then it quickly accelerates to the release point. So the penalty function method achieves a serviceable result, but it has some flaws. The tweaking of the different variables, mu, gamma, beta, etc., is very finicky. In the version I got to work, they range from 50,000 to 0.001, so the tuning process is non-trivial. The code is very slow. In fact, I had to cap it at 6,000 iterations because it takes so long to run. The version I've displayed here hasn't actually converged because I had to cut the iteration short. And lastly, the constraints are soft. The final result we see stays within the bounds, but throughout the learning process, it frequently exceeds the bounds. If we were using this to train a physical robot with actual joints that can't go beyond specific angles, then this process wouldn't work. I used penalty functions to constrain the states, but there's another method to constrain that I could have used instead. If we know that the arm will lie within the bounds for some time, then move to a position where it's on the boundary, then leave the boundary line, we can create a split interval algorithm where we perturb U while still satisfying the constraints. This method is more accurate and runs faster, but it's also more difficult to implement. So for this particular project, it was out of scope. So final results, how did we do? The launcher is able to get close to the target. However, because it's not able to exactly match the x and y velocities, it doesn't hit the target exactly, especially for targets that are farther away. For the unconstrained case, the integral of the cost was a little over 9,000. For the unconstrained case, it was almost 18,000, so almost double. This makes sense since the arm can't build up speed over multiple iterations, multiple revolutions. With low input, it needs a higher input in the constrained case to quickly accelerate. And then we were able to achieve a motion which shares some properties with a human throwing motion. It's interesting to somewhat confirm the hypothesis that the natural human motion is optimal. Finally, these were the sources I used for this project. Thanks for watching, and I hope you found this interesting.